Okay, so in this video, I'm going to solve a problem from Putnam 2019. It is the A3 problem A3 from 2019. So it says you have a set of numbers B0 through B 2019, and then it gives you a polynomial with those coefficients of degree 2019. They give you that the leading coefficient is non-zero, which means that polynomial has exactly 2019 roots, some of which may be equal. And then they take the average of those roots, average of the absolute value of those roots. And then they're asking you to essentially find the minimum possible value of this average. So what is that? What is the largest possible m such that mu, which is the average, is greater than or equal to m for all choices of B0 through B 2019 with some given condition. So there, the order of the coefficients is given. So they are increasing order. So by the way, this m may not be minimum, it could be infimum of the average of the coefficients. Maybe the average of coefficients doesn't have a minimum, but they may be getting closer and closer to a value of m. So if you look at the average of coefficients, the average of the absolute values of the coefficients, essentially what we are trying to do is that to show that they're getting closer to some value, and either that value m can be reached or it can be approached. Okay, so it takes quite a bit to even like kind of understand what exactly the question is asking. So you have to like think about this and then see what exactly it is asking. So to simplify things, I'm going to consider some small cases, as I often do. So looking at the problem, the 2019 may be an arbitrary number, or it could have something to do with the fact that 2019 is odd, or maybe the fact that it's divisible by 3, or something of that sort might become significant in solving the problem. But not knowing anything about why 2019 is important, I'm going to start looking at some examples. So instead of a polynomial of degree 2019, I'm going to look at a linear polynomial, and then a quadratic, and then a quartic, and see what I'm going to be able to get. Just to simplify the problem and see what can be done. So I'll start from degree 1. So degree 1 gives me a condition that, so I'm going to replace this one by n, and n would be the degree. So if n is 1, it would look like that, and the inequalities are going to be this. But that's impossible. So that's a contradiction. So you can't have B0 and B1 between 1 and 1 when they are not equal. So that's not going to work. Okay, so that's kind of a silly case. We just have to ignore that case. But starting from the next case, those are quite real. So if you take the polynomial that is quadratic, so b0 plus b1z plus b2z squared, then you're going to get 1 less than or equal to b0 less than b1 less than b2 less than or equal to 2. So certainly we have b0, b1, b2, and we are trying to find the average of absolute values of the roots. So looking at the roots, you have 2 roots for the polynomial, and we are trying to find the average of these 2. So z1 plus z2 over 2. Although you could kind of, ignore the average and just look at the sum and then divide by 2. That's also possible. Okay, so since I have a quadratic, I can just find the 2 numbers z1 and z2, 2 roots of z1 and z2, using quadratic formula, and then plug it in here and then like see what I get for the absolute values. This is probably not a very good idea, because if I use quadratic formula at this point, I may get an insight into quadratic equations, but I'm not going to be getting an insight into cubic or quartic or things that are of higher degree, because I don't have a formula for those. I don't have an explicit formula for finding the roots. Instead, I'm going to see if I can somehow relate this with the coefficients. If I have the sum of the absolute values, can we relate that with the coefficients? So can we relate this average with B0, B1, B2? Okay, so I know if I did not have the absolute values, I could. So I'm going to see what I would be able to do. So remember that if you have a complex number, the absolute value is the distance to the origin. So evaluating the absolute value is not going to be as easy as just like considering whether it is positive or negative, because there is no positivity or negativity for complex numbers. Instead, what I need to do is to see whether these are real or not. So if Z1 and Z2 are real, so if Z1 and Z2 are real, then I know the sum of the two roots, Z1 plus Z2, is negative B1 over B0, which is negative. And their product is B2 over B0, which is positive. Okay, so that's nice because I have two numbers, their product is positive, and their sum is negative. So that means Z1 and Z2 are both negative. So because of that, I can actually find out what the sum is. So I'm looking at negative of that divided by 2. So negative 1/2. Z1 plus Z2 is negative B1 over B0. So that is, I'm sorry, I should have said B2 at the bottom. So I have to swap these. Yeah, B2 is the leading coefficient. So this is product is B0 over B2. Okay, so negative B1 over B2, which is B1 over 2B2. But I know B1 is more than B0, which is more than or equal to 1. So I can say the minimum of this is 1. And for the other one, the minimum is 2 times 2, because the maximum of B2 is 2. So that's 1/4. And I don't have equality here because I don't have equality here. So that would be a strict inequality. So far I got that maybe the answer is 1/4, but I would also need to come up with an example that gives me numbers that are close to 1/4. So that may or may not be possible, but I wouldn't know the answer is 1/4. I would have to first look at the other case. So let's look at the complex case. Let's look at the case where it is complex number. So when it is complex number, I'm going to get absolute value of Z1 plus absolute value of Z2. Okay, so that case seems a bit more complicated because in that case, I'm not really able to identify whether they are positive or not. But I know for complex numbers, I know for quadratics, the two complex roots are complex conjugates of each other. Therefore, they have the same absolute values. So if Z1 and Z2 are not real, then Z1 and Z2 are going to be complex conjugates of each other. Z2 is complex conjugate of Z1. And therefore, their absolute values are the same. So the absolute value of Z1 plus absolute value of Z2 is just going to be twice absolute value of Z1. But again, I'm trying to relate these with the coefficients. So I can say this is twice square root of their product. but their product is, I know exactly what the product is. B0 over B2, that's the product, which is at least 2 over root 2. And if I divide by 2, I get absolute value of Z1 plus absolute value of Z2 over 2 is greater than or equal to 1 over root 2. Okay, so that's nice. I'm going to compare this guy with this guy and see what I get. So that was interesting because I think I missed the divided by 2 here. Yeah, I missed the divided by 2 because, yeah, I guess it doesn't really matter. So I divided by 2 here, then divided by 2, so that becomes 1 over root 2. Okay, yeah, so not a problem. That's just basically the same thing. So I got 2 different answers for these. One of them gave me 1 over 4. The other one gave me 1 over root 2. So let's see if I can somehow reconcile that. If you think about the second one, of course, this equality and this equality fails if you are working with real numbers, because you could have 2 roots. One of them is -5, one of them is -3 potentially. I mean, it may not happen in this case, but you could have 2 roots that are negative, but they don't have absolute values that are the same. So I can't really say that this is equal to absolute value, twice absolute value of Z1. But I do see there's a relation here, because looking at this part, this is an arithmetic mean, and looking at this part, this is the geometric mean. And if you aren't familiar with this, let me remind you of an important inequality. For all positive real numbers x1 through xn, the sum of them divided by n, that's called arithmetic mean, is at least geometric mean. So this is the arithmetic mean, and this side is the geometric mean. Furthermore, equality only holds if and only if all of those positive numbers are the exact same thing. If they're all the same, then you have equality. And if at least 2 of them are not the same, then you don't have equality. Okay, so how is that going to help? Because I can relate these 2 now. So now in general, I can say, well, absolute value of x1 plus absolute value of x2, z1 plus absolute value of z2 over 2, that's greater than or equal to root z1, z2 in absolute value, which is equal to root constant divided by the leading term, which is 1 over root 2. So in both cases, I was able to actually get the 1 over root 2. So this inequality is valid for both real and complex and the non-real case. But you would have to come up with 2 things here when you're dealing with a question of finding the minimum or finding the infimum. The 2 things are, first of all, that average is at least 1 over root 2. And second of all, there is an example that gives you 1 over root 2. Or there are examples that give you 1 over root 2 plus a little bit. Like let's say 1 over root 2 plus 1 over n for every n. So we are able to get close to 1 over root 2, but we are not going to be able to go beyond, below 1 over root 2.